Welcome everybody to today's Flow seminar. As all of you know by now, Flow stands for Federated Learning One World Seminar, and we run this on a weekly basis on Wednesday at various times, typically 1 p.m. UTC. Sometimes we adjust depending on the location of the speaker. We have this goal of catering for everything related to federated learning, which includes theory, applications, systems, algorithms, novel architectures, so anything to do with federated learning. And so far, we've focused on a few of these subfields. We'd like to go into some other subfields as well. We have still a long road ahead of us. We've run this roughly for a year now. We started in May last year, and we already had more than 40 talks. I don't know exactly which one is this one. Maybe Samuel will help me out, but this is 40 plus.
42nd.
42nd, okay, 42nd. That's great. Today we have great pleasure to welcome Laurent Condat as the 42nd speaker. Laurent is a research scientist here at KAUST, and so he spent quite a bit of his time in France because that's where he was born and where he spent much of his career in Grenoble at CNRS, and from Grenoble Institute of Technology. I think it's called Grenoble Institute of Technology, right?
Yes.
So you got your PhD.
And there is University of Grenoble Alpes, but yeah.
Yeah, so in 2006.
Complicated, so as you know.
some 15 years ago, and there was this brief spell when Laurent spent 2 years in Munich, Germany, and a couple years ago he moved here to KAUST, and we're very grateful to have him around. So he's expert in several domains, including image signal processing, optimization, monotone operator theory, convex and non-smooth analysis. Did I mention inverse problems? If I did, this is the second time. If I didn't, okay. So on stuff of this type, and stochastic optimization is a new area that he's focusing a little bit on recently. And today, Laurent will talk about his recent work on local SGD and local fixed point methods, and with the aim of understanding what these local methods, such as local SGD, actually do. So this is a good topic for federated learning seminar. Samuel will maybe say a few words about how we're going to handle the Q&A. So this we do routinely. Samuel, can you again show up and say a few words about this? And I do not know whether okay, just go ahead.
Yeah, we already discussed. So Laurent agreed that you can take questions throughout his talk. So if you have any questions, so don't hesitate to either post it to chat and set visibility to everyone, or in the participants menu, you have an option to raise hand. And if we see that there is some raised hand, I'll try to unmute you and you can ask a question yourself. And also the same with the chat. If we see the question, we try always to unmute the person so you can have a bit of an interaction with the speaker.
Okay, great. So Laurent, take it away.
Thank you. So thank you, Peter, for this opportunity to present my work and for the kind introduction. So as you said, yeah, I'm a research scientist in KAUST. So I arrived 1.5 years ago. So yeah, before that, I worked on more non-smooth optimization. So I'm kind of new in machine learning and related topics. So this is the first work I did when I arrived 1 year ago. So which was presented at ICML with this title, From Local SGD to Local Fixed Point Methods for Federated Learning. And the main idea is to extend methods like federated averaging or local gradient descent to the more general setting of fixed point methods. So this is joint work with Peter and 3 talented students in the group. So Gregory primarily, who was the first author of this work. of the paper, and Dmitry Kovalev and Elmur Gazer. So this is the outline of the talk. So I will start with reminding you the setting, which is the setting of distributed and federated learning. So most of you are familiar with these ideas of distributed computations and communication with the concerns that we have in federated learning, but still I will spend a bit of time recalling this context, and then I will present the general problem formulation using fixed point operators and motivate a bit this work. And then I will propose two algorithms and describe the convergence results that we obtained. So we place ourselves in we will consider a distributed setting in which we have a number of machines or nodes doing computations in parallel. So there is capital M nodes, and they all communicate with a server or master. So we have this master client architecture. So the machines can communicate back and forth with the master. So this is a distributed but centralized setting. And in particular, we are interested in federated learning. So federated learning is this recent paradigm in which we have a huge number of users involved in some global machine learning task in a collaborative way. So each user has a device like a computer, a laptop, or a mobile phone, and they communicate with a distant server, which is, you can think of some service in the cloud. And for instance, so you can think of some text prediction, for instance, by Google. So if you type a message on your phone, the app will predict the next words that you are likely to type. Or if you do a search in Google, it will suggest the completion of the sentence. So like I tried to illustrate. So I typed I want, and it proposed I want to hit your pancreas. Okay, why not? It seems it's the title of a movie. So yes, there are plenty of applications like this where you have a huge number of users which are involved in this collaborative task of learning or training a global model, which can be the weights of a neural network, for instance, which will have good performance globally, taking into account all the data stored locally by each user.
So I have first question, Laurent.
Yep.
I mean, did you watch the movie?
No.
That's all.
So I don't know why. I tried to think about why he proposed this movie.
I've never heard
Maybe
of
this is because I looked for movies recently, so it proposed a title of a movie starting by I want. Maybe there are not so many titles started by I want. So yeah, propose this movie.
Maybe
I think it's Japanese anime.
Want to recommend it or something? Okay, so you didn't see it. All right, good. Thank you.
But my pancreas is fine. So it's not related to that. Okay, so yes. So this is an example, text prediction. And yeah, as I was saying, so the first issue is communication. So communication from a mobile phone to over the mobile network can be slow and costly. So we want to minimize the communication load, the overall communication load, which is necessary to achieve a given accuracy on the global model. This is the first issue, and the second issue is privacy. So users don't want to share their data; they just want to send the minimum amount of information, which captures just the information which is necessary for this training task. So they want to keep their local data, whatever there are, their messages for text prediction, their images for image classification, and so on. they want to keep all this data private. So we want to communicate. So the communication is really the bottleneck. We want to decrease the amount of communication. Another example which I can mention is healthcare, for instance. So you have hospitals which have, each hospital has all the data of its patients. And we can imagine that there is a National Health Institute that is interested in learning some protocol to care like the COVID, for instance, based on all the data available at all the hospitals. But again, for privacy reasons, so hospitals want to keep this data private and just communicate the right amount of information which is needed for the learning task. So we will model the setting like this. So we have this capital M number of nodes, which can be arbitrarily large, and at each node number I, there is we model the set of computations which are done locally by a mathematical operator denoted by TI. So TI is the set of computations that can be done locally during an iteration of the learning process. And the goal in this setting is to find a fixed point of the operator T, which is the average of all these TIs. So we define, so X, the variable that we are looking for is the model. So it's a vector in RD for some D. And capital M is the number of users. That can be arbitrarily large. So we define T as the average of all these operators Ti, which could be a gradient descent step with respect to some loss function with respect to the local data stored by the user number I, for instance. And the goal is to find a fixed point of T. So a model, a global model X star, such that T of X star is equal to X star. So the baseline algorithms to do that, to find a fixed point algorithm, fixed point X star of this general model, general fixed point operator T, is this one. So very standard algorithm. So at each iteration number K, the master first sends or broadcasts the model, current estimate of the model xk to all users, all nodes. Then each user applies its operator Ti, which models a set of computations which are done locally, Ti. So it applies Ti to xk. And this way it obtains a local model, xi of xi, yeah, k plus 1. So after the case iteration, each user has a different model xi k plus 1. So there is no notion of homogeneity. Okay, so these operators Ti can be arbitrarily different from each other. So we are really in a completely heterogeneous setting. So the Ti can be arbitrary operators. So after applying this individual operators Ti, each user has its own model. Then they are all sent to the master. And the only operation done by the master is this aggregation by averaging. So the next estimate at the next iteration of the global model X is xk plus 1 is just the average of all these received local models xi k plus 1. So mathematically, we can write the fixed point iteration as in this simple form. Xk plus 1 is just T, this average operator, applied to xk, because it is indeed the average of the output of the TIs applied to xk. Okay, so this is a standard algorithm, but we have to keep in mind that it's costly in terms of communication. There is a broadcast operation, and also which might be cheap, but the most costly operation is this transmission step in which all users has to send its vector at each iteration to the master. And this is this communication steps that we want to reduce. So as a simple illustration, so the most simple setting is when we want to find a minimizer of a smooth function, which is a finite sum, an average of functions fi. So this could be the loss functions with respect to local data. So, and ti is the gradient descent operator, gradient descent step, which takes the difference between x and the gradient of fi applied to x with a step size gamma. So we can write it as a particular case of this fixed point operators. We have xk plus 1 is the average is t to apply to xk, which is the average of the ti's applies to xk. We can put x, which is common to all nodes outside the sum. So this is xk minus step size times the average of the fi's. But the average of the gradient of the fi is the gradient of f, so the global cost function, because the gradient of a sum is the sum of the gradients. So it's mathematically it's the same as taking a gradient descent step with respect to the function global functions f in the first place. So this is the most simple example, but there are plenty of other applications of this fixed point setting. So in optimization, first, we can think beyond the minimization of a smooth function using its gradient. We can think of proximal algorithms, which make use of the proximity operator, or primordial algorithms, where there is not only the model X as variable, but there are also dual variables, which enter into the iterative process. Cyclic gradient descent, this is when each user has its own finite sum, and the operator which is applied is gradient descent applied in cyclic order over all the data points. Block coordinate methods, methods with inertia, higher order methods, they are all examples of methods which converge, which are iterative methods converging to a fixed point. And beyond optimization, we can also think of finding a saddle point of a non-convex, convex concave function, finding a steady state of a PDE, an eigenvector of a matrix or system, or we can also solve monotone inclusions, variational inequalities, and so on and so forth. So this fixed point setting really captures a wide range of applications beyond optimization. Okay, so I remind you that our goal is to decrease the communication effort. So to do so, a natural idea is to use this so-called local steps. So we will see what they consist in. But the idea is just to remove the communication step. So the iteration of the local fixed point method starts like for the baseline algorithm. The master sends the current estimate to all nodes. Each node applies its operator ti to xk. So this way it obtains xi, its own local model xi k plus 1. And now we don't communicate as before. We just keep on repeating this process of applying the local operators. So now the user number I is offline. It's separate from the rest of the world, and it applies its operator ti again to its local model this time. So we have xi k plus 2 after k plus 2 iterations. It's ti applied to the previous local model xi k plus 1, which was itself ti of xk. So it's ti of xk. Okay, so the local operator has been applied twice to the current estimate that was known at iteration number k. Okay, so this idea of doing local steps is this idea of applying this operators ti, which could be gradient descent or any other fixed point operators, to the local model repeatedly. And eventually there will be the communication step as before, but after a certain number of local iterations, local steps, that is larger than 1. So for instance, 10 after there is communication every 10 iterations instead of after every iteration. So this way, it's a straightforward way of decreasing the communication effort, because now you communicate every 10 iterations instead of every iteration. So this algorithm is not new. So what is new is a generalization, the expression here in the general setting of fixed point operators. But in the case of gradient descent, where each ti is a gradient descent step with respect to a function fi, this algorithm is known and widely used by practitioners. And it is called local gradient descent, because it's gradient descent, but applied locally with several local steps, several iterations of gradient descent before communication. So it has been studied recently. There is a growing literature. So this list is neither exhaustive nor up to date. So yes, there is a growing literature analyzing local gradient descent. It's also called federated averaging, and all the variants. So you can imagine lots of variants with additional compression of the vectors, with partial participation of the nodes, and so on and so forth, using proximity operators instead of gradients of non-smooth functions. And there are many extensions appearing in the literature regularly. So our first contribution here was to generalize the algorithm to the fixed point setting. So here it is, this is algorithm 1. So as you see, it does what I explained in the previous slide. So at every iteration, so k is the iteration counter, there is at every iteration, there is the ti, which is applied to the current estimate xik. So there is actually convex combination here between identity and ti, which is applied. So there is this under-reaction parameter lambda, which is useful to prove convergence in the non-strongly convex non-contractive case. So, and we don't communicate at every iteration. Here, the algorithm has been written with synchronization times, Tn. So n now is a counter of communication rounds or counter of epochs. So an epoch is a set of local steps, a set of iterations at which there is no communication. So the synchronization times are the indexes of iteration at which there is communication. So if k, the iteration counter, is one of the synchronization times, there is communication, else, so there is no communication, and the algorithm proceeds with its local model at the next iteration. And at the master, if the iteration index is synchronization time, then the master receives and aggregates all these local models and broadcasts them at the next iteration. But if not, then the master does nothing. There is no communication. So, an epoch, number n, is the sequence of iterations between two synchronization times. So the synchronization times are the indexes of the iteration indexes at which communication occurs. So here the algorithm is written in a general way, so that is the synchronization times can be arbitrary, but to analyze the algorithm, of course, we need to communicate once every certain number of iterations. We cannot wait indefinitely before communicating. So the number of iteration in each epoch is supposed to be bounded, to be upper bounded by some integer h. So one example was the simplest way is to take the uniform synchronization times, that is Tn equals nh. N is the epoch index and h is the number of iterations in each epoch. So there are here h local steps, h iterations in each epoch. If h is 1, this is a baseline algorithm communicating after every iteration, but the idea is to take h larger than. So you can interrupt me if there is any question in this on this algorithm. So we have this double loop structure of epochs and iteration inside each epoch. So the outer loop is on the epochs, at which, and at the end there is communication at the end of every epoch.
So I will interrupt you with a mock-up question, if I may.
Yes.
So just trying to represent maybe silent minority.
Sure.
Here. Okay. So what is the motivation behind this work? Why do you want to analyze this in this fixed point setting? What is the main motivation rather than let's generalize something?
So yes, the first motivation was to capture, to go beyond gradient descent with respect to smooth functions. So we could think of using proximity operators. So if we take an average of proximity operators, it's something which is called the proximal average. So it's something which has some nice properties. So the fixed point is not the minimizer of the sum of the functions. In that case, something a bit different, but yeah, so we can go from smooth optimization to non-smooth optimization first. And then we could think of other types of operators like projection on sets. If we project on sets and average, it's called parallel projections. So it's something which is well known also in the literature of convex optimization. We could go to non-convex operators. So like if we take cyclic gradient descent with respect to a local set of samples at each user, then it's beyond already the local gradient descent setting. So this was the first motivation, like to capture wide range of operators. But there is a second motivation, which is that which is a kind of parsimony idea, which is that using a minimal set of assumptions, we could analyze algorithms. So we can analyze gradient descent, for instance, but just by viewing it as an operator. So we will not be reasoning on the decay of the objective function or some fancy Lyapunov function. Here we just have at our disposal the convergence in norm. So this way we can analyze local gradient descent, but from a wider perspective. And this is actually what we did, and we obtain results which are new, even in the case of gradient descent, as we will see in the next slide.
And that's your. I'm continuing with this mock-up just with one more. So people say that for these local type methods, local gradients and local SGD, there's this notion that this belief that the heterogeneous data setting is difficult for analysis. That somehow once you have heterogeneous data, which in this case would mean you have different local operators, they're not the copies of the same operator in any way, then something goes wrong. So does this work shed some light on this?
Yes, I think it will be clear in the next slide. Yeah, I will. Please ask again your question in a minute if it's not clear, but that's what I'm going to show. So that's what I want to show. Yes, it's.
All right. So
it's not the.
Oh, the next slide is okay. I don't know what the next slide is. This is going to.
You're spoiling the talk.
All right.
But yeah, I hope it will be. This is what I want to show, that it's this setting is well defined mathematically, and we will be able to prove convergence in the arbitrarily general case, with arbitrarily heterogeneous case. Yes, and we will see that this heterogeneity, it enters only in the discrepancy between the obtained solution and the ideal solution. Yes, this distance can be large, but we can bound it and can characterize this distance. Yes.
Thanks.
So let me start with the analysis now of this algorithm. So here, so there are several results in the paper, but here I'm going to describe the main one, let's say, which is a case where each operator is contractive. So a contractive operator has this property that it's also called Lipschitz continuous with a constant key, which is smaller than 1. That is, it shrinks the distance when it is applied. So if the distance between ti of x and ti of y is smaller or equal to the distance between x and y multiplied by t, t is smaller than 1. So each time you apply ti, you get a shrinkage of the distance by a constant factor. So all TIs are supposed to be contractive with factors, same factor, t. And for the simplicity of the analysis, also the synchronization times are uniform. Yeah. So n is an epoch index, and h is the number of local steps inside each epoch. So, and lambda, the relaxation parameter in the algorithm is not needed here. We can set it to 1. It's the best choice. So it simplifies the analysis, and it gives the optimal rate. So to analyze algorithm, actually, here is so everything is in this definition, which is important. So we define this tilde t as being the average of the TIs composed, so to the power of h, which means composed themselves h times. So because we have seen that, let me show you the algorithm again, like here. I said that TI is applied repeatedly. So if it's applied 2 times, for instance, h equals 2, xi k plus 2 is TI applied to this variable, but it is already TI applied to xk. So it's TI applied to TI applied to xk. So TIs composed with TIs 2 times. Okay, so this is what is denoted here by this power of h. It's the composition of TI with itself. H time, it models the fact that TI is applied repeatedly locally. And communication, so aggregation, which is mathematically just averaging, occurs at the end after these operators have been applied in parallel H times locally. So the operator tilde t models what happens globally in one epoch of this local fixed point algorithm. So we can write that x at, so the at denotes the fact that this is a variable known as the master. So the next estimate of the solution, x at n after n plus 1 at the end of the n plus 1 epoch. So the number of iterations is n plus 1 times h, number of local steps, number of iterations in each epoch. So it is equal to this operator tilde t applied to the previous estimate. So with this simple formulation, is there a question? I see. Yes. Yeah, I can read it. A question of Constantine asking.
So
I already tried to unmute.
Yeah, yes, please.
So we like to hear some other voices, so we'll unmute people so they can talk.
Yes, sure.
So, yes, small question about, I have wrote it. So I an assumption about uniqueness about stationary point for tilde t, because if tilde t is some linear operator, it can has a series of several like eigenvectors. And do you make any assumption about how much stationary points t tilde have or no, or it should be unique for purpose of analysis?
So In this setting, it is going to be unique. Yes, exactly. This is general properties of so-called Picard iterates of contractive operators. So if we have contractive operators, and here I'm going to show in the next slide that this tilde t is contractive, then the fixed point exists and is unique. This is a property of contractive operators. So in the more general non-expansive setting, it's not necessarily the case. Yes, you have to assume existence of a fixed point, and then it need not be unique. But the algorithm will converge to one particular fixed point if it's not unique. But here, yeah, so the fixed point automatically, without any assumptions, exists and is unique. We just assume that all the TIs are T contractive. That's the only assumption. Yeah.
Okay.
Yes, this is a good question. Are there any other questions? Okay, so let me continue with this main convergence result. So here it is. This is a theorem 2.11 in the paper. So yeah, as I just said, the fixed point of this operator tilde t, modeling what happens in a global outer iteration, a global epoch. This fixed point exists and is unique, so we call it X dagger. And the algorithm converges exactly to X dagger. So Peter was asking about some notion of heterogeneity that the algorithm could possibly diverge, but no, it does converge in all cases to this fixed point X dagger. And it converges linearly and with a rate which is k to the power of h. So k is smaller than 1. So the smaller the better. So if the contraction factor is small, the algorithm will converge very rapidly, even to the point that if it's 0, the algorithm converges in one step. So tilde t is k to the power of h contractive, which is good. So as h increases, the k to the power of h is smaller and smaller. So we have an algorithm that converges at every epoch. The contraction factor is k to the power of h. So, but there are h iteration in each epoch. So it's the same as saying that the virtual contraction factor at every iteration is k, like for the baseline algorithm. So we have an algorithm that converges at the same rate, which is k, than the baseline algorithm with communication after every iteration. So the algorithm converges and the rate is the same as with or without communication, which is good. But as you guessed, yes, there is no magic. There is no free lunch. So there is a price to pay, and the price to pay is that X dagger is not X star. So X star is the ideal solution, the fixed point of T, the average of the TIs. This is the models the global models that we would like to estimate. But here the algorithm converges and converges rapidly to a point, but which is not X star. So the next question is, can we characterize this distance between X star and X dagger? And here is the characterization that we obtained, which is new in the literature, even for the case of local gradient descent. So the previous theorem is new, to my knowledge, was new. And this one as well. So it says that the distance between X daggers, obtained solution, and X star is bounded by S, and this formula is somehow tight. So what is S? So there is the rate, the contraction factor T equals to Xi here, which appears. And there is this factor here where the number of local steps appears, and the average of the distance. So here the notion of heterogeneity appears. It's the average of the distances between the local operators applied to X star. So the kind of discrepancy between the output of applying Ti to the global model X star, which means somehow the fact that the loss function is different, the local loss function is different from the global loss function. So if by applying the local operators Ti of particular user number I applied to the global model, you obtain something different from X star, it means that the local data attract the global model towards a local minimizer, which is different. So this discrepancy here appears in this, under this form. So we can have a look at what this value S represents in some particular cases to convince ourselves that it is somehow tight. So if there is only one local step, then S is 0. So this is visible here in the fact that we have 1 minus something to the power of 0. So this is 1 minus 1, 0. So there is so X star is equal to X dagger for the baseline algorithm in which you apply only one local step. So it's tight in this sense. If we are back to the setting in which we communicate at every iteration, there is no error. If there is only one node, one user, there is also no error. S is 0. It's because the Ti is equal to T, the global model. So we have that T of X star is equal to X star. So this term here, this discrepancy is 0 just because there is no notion of heterogeneity if there is only one user. If in the homogeneous case in which all Ti's would be equal to T, which is not very interesting here in this deterministic setting, but for the stochastic extension, it could be interesting. But yeah, in that case, S is 0. And also if the contraction factor is 0, it means that the algorithm will converge in one step. So it's obviously, the error is obviously 0 also in that case. And on the other hand, we can have a look at what happens when H, the number of local steps increases. So from 1 to plus infinity. Then this value S, this upper bound S, increases as well monotonically from being 0 to something which is not infinite, which is finite, this value S infinity, which is the same when you remove this factor, which is smaller than 1 here. So if there is somehow an infinite number of local steps, then so yeah, virtually you apply a very, very large number of local steps, and then you communicate only at the very end. What happens in that case? It will happen that every user has converged to its local model, which is a fixed point of its operator Ti. So by applying Ti repeatedly, so the model will diverge from X, so the global model, and will be attracted by the local solution, the local optimum. And eventually, each user will compute its local solution, its locally optimal model, and the global model will just be the average of this local model. So then the discrepancy, the distance is finite, and it can be characterized like this. It's upper bounded by the average of the distances. Okay. So as a corollary of the two previous theorems, we can characterize the convergence to the exact solution X star. So we have linear convergence to the, we can look at the second formula. So we have linear convergence with the rate t to the power of h. So this first term converges linearly to 0. But there is this plus s, the neighborhood size. So the algorithm converges to in a neighborhood of the exact solution, X star, linearly. Okay, so the algorithm always converges rapidly with this convergence rate t to the power of h. But it converges in a neighborhood of the solution. So we can illustrate this by some experiments. So this is exactly the behaviors that we observe in practice. If we look at the convergence with respect to the number of iterations, whatever the number of local steps, the convergence speed is the same at the beginning. And then there is a saturation, which means that the algorithm has converged, but it has converged to something which is not the ideal global solution X star. So that's why this objective suboptimality does not tend to 0. Okay, so the algorithm has converged, but to a value which is not the global solution. And the discrepancy is larger if the number of local steps is larger. If there is only one open steps, then the error tends to 0. So this is the behavior with respect to the number of iterations. So as I said, the conversion speed is the same, whatever the number h of local steps. But the algorithm does not converge to the ideal solution if the number of local steps is larger than 1. But if we look at the convergence with respect to the number of communication rounds, which is what matters if communication is the bottleneck. So if you want to measure the number of communication rounds needed to achieve epsilon accuracy on the global, on the true solution, then we see that these curves are just the same as on the right, but stretched by a factor of h. So convergence is indeed h times faster, because the contraction rate, the linear convergence rate is t to the power of h. So convergence is h times faster by using a large number of local steps, which is good. But again, the price to pay is that it will eventually converge, but not to 0. It will saturate when they achieve this solution X dagger, which is different from X star. So another illustration of this phenomenon is this one. So here we have X stars, the models that we would like to achieve. X dagger is the solution to which the algorithm converges. So we can imagine that the green ball is a ball of radius epsilon. Epsilon is the accuracy that is that we want to achieve. So if X dagger is in a ball of epsilon accuracy of X star, so that the distance between X star and X dagger is smaller than epsilon, then we will achieve epsilon accuracy after a finite number of iteration of epochs. And we will do so h times faster than with the baseline algorithm. So each dot represents the model estimate at the server after one communication round. So this is after some number of steps, we will achieve epsilon accuracy with the baseline algorithm. But with the new algorithm, we have the red points. So we have h equals 3 in this illustration. So we have 3 times less points. So we will need 3 times less epochs, communication rounds, to achieve epsilon accuracy, because these 2 points here and here are equally valid in the sense that they're all at epsilon distance, epsilon accuracy from the global ideal solution X star. Okay, so it works. Using local steps is indeed a way to achieve epsilon accuracy h times faster. So we guess that there is some trick here. And the trick is that if we express the complexity in terms of epsilon accuracy asymptotically when epsilon tends to 0, if we are interested in the regime in which epsilon is small, so we want to achieve a solution at high accuracy. So if we let epsilon decrease, of course, X dagger will not be in the epsilon accuracy ball anymore. So if we write the complexity, we have the conditioning L over mu, the Lipschitz constant over the strong convexity constant for the case of local gradient descent, divided by h. So we have this division by h of the complexity in terms of communication rounds to achieve epsilon accuracy. But if epsilon decreases, we will have to. So h depends on if we increase h, then the discrepancy between X dagger and X star increases. So in other words, if epsilon tends to 0, H must tend to 1. So we are back in the regime in which we communicate after every iteration. So the complexity with H tending to 1 is back to kappa log of 1 over epsilon. So it is what we observed on the previous slide. If we really want the error to tend to 0, then we are obliged to take H equals 1, because what we have just proved is that the algorithm converges, but not to the exact solution. So if we want to obtain the exact solution at high accuracy, it's not appropriate. Do I have time? Maybe I can accelerate a bit. So in the paper, we also have other convergence results in the non-contractive case, so in the case in which the operators are merely non-expansive. So we can prove convergence as well to a fixed point, assuming it exists. But we have to use some kind of under relaxation in that case, and the rate on the fixed point residuals that we obtain. So we measure the error as this distance between x, k, and applying t to xk. So this is called the fixed point residual. In the case of gradient descent, this would be measuring the norm of the gradient of the global function f. So this will tend to 0 at a sublinear rate. And here the acceleration factor of h is not guaranteed anymore. There are cases in which the algorithm is not faster. So the interest of the algorithm is not so clear anymore in the non-contractive case. So we also proposed a randomized version of this algorithm 1, in which instead of having this say fixed number of iterations in each epoch, then the fact of communicating or not is decided by flipping a coin at each iteration. At each iteration, with probability P, we communicate or we don't. So P can be, P here will play the same role as 1 over H number of local steps in the algorithm 1. So we observe the same behavior, we have the same properties as with the deterministic algorithm, but we have additional oscillations around in the neighborhood of this X dagger solution. So not only does the algorithm converge to something which is not the ideal solution, but there are additional oscillation around this solution. So I would say that the algorithm 2 with the randomized strategy is less interesting than the deterministic algorithm with a fixed number of local steps. So it's interesting to parallel this with what we observe with the SVRG, for instance. So we have this loopless version of SVRG in which we decide exactly by flipping a coin whether we take the full pass over the data or not. So SVRG is an algorithm to compute the minimizer of a finite sum of functions. And it was proved that the loopless SVRG, the randomized version, is more interesting. But here, the converse, the randomized strategy is not interesting in this context. It's better to take a finite number of local steps. You will avoid these oscillations here. Okay, so this is a proof of convergence for the randomized algorithm. It's similar. We have linear convergence with this factor, which depends on the probability P, up to a neighborhood of the solution. But the analysis is less tight here. We have this huge constants like 150, which appears here. But qualitatively, it's the same. We have linear convergence up to a neighborhood of the solution. Okay, so to sum up, using local steps was proved to be a good strategy. If the goal is to obtain a medium accuracy solution, we can use local steps, and we will obtain such a solution with medium accuracy faster than using the baseline algorithm in terms of measuring the number of the communication load. So in all applications where communication is a bottleneck, it's indeed a good idea to use local steps. And we can even, if we really want a high accuracy, we can decrease h along the iterations up to 1, and the algorithm, when h is 1, will eventually converge to the true solution, of course. So even as a kind of initialization strategy to accelerate the convergence at the beginning of the process, it's a good idea to use local steps. So in this talk, I did not cover the case where the operators Ti are stochastic. Here they were deterministic, but it would be interesting to study this more general setting. So the promise of the title is not completely covered. So the title was from SGD to fixed point method. So the S is missing. But we should do it as future work. And yes, there is of course a question of reducing this variance, this discrepancy between X-dagger and X-star, so the obtained solution and the true solution. This is what is achieved by scaffold, for instance. So yeah, there are many questions around this idea of trying to reduce the variance. But yeah, it's not clear to me that that this is really the way to do to combine local steps with the variance reduction. So yeah, it's an open question, at least for me. So thank you, and yeah, we have time for questions.
Thank you, Laurent, for the very nice talk. Anybody who has questions, feel free to raise your hands, not physically in your rooms because we can't see that, but virtually by clicking on the right icon. Or you could just type something if you can't find the raise hands feature.
So Peter, did I answer your questions, mock-up questions?
Yes, thank you. You did. Thank you.
So it's true that if we reason on the complexity with respect to epsilon, yes, the rate at the very end is just kappa log of 1 over epsilon. So it's the same complexity. So there is no gain of using local steps over the baseline algorithm if the goal is to obtain epsilon accuracy for an arbitrarily small epsilon. So, but yeah, as I said, if for medium accuracy, we can indeed obtain an epsilon accuracy solution
and
faster.
And that's the whole point of this communication reduction strategy through local computation, right? The whole point is that in the case where you don't want high precision, you can reduce communication by simply doing more local work. And the less precision you require, the more local work you can do to achieve that. So that's precisely the point here. And unfortunately,
Exactly.
machine learning, you don't typically require high accuracy, and this is why this is useful strategy. But I also want to highlight for everybody that here this happens even in the heterogeneous data regime,
Yes.
which is modeled by these operators being different, whereas the standard federated averaging analysis would require these TIs to be identical, or at least to be formed from samples from the same T or something of that type. So in the homogeneous data set.
Yes, this behavior that we observe here is not a coincidence. It's not because we took a particular data set of functions. It's proved by the theorems to always happen, in the sense that it's proved that we have this contraction factor, which is this constant to the power of the number of local steps. So the behavior will be always the same as what is illustrated here on the left.
Okay, so we have a question by Eton. So you can unmute yourself now, I believe.
Okay. Thank you, Peter. So, thank you for the very nice presentation. My question was about the experiment. So maybe I missed the
No,
point.
yeah, you're right. I did not say anything about it. So here, this is just a local gradient descent in this particular figure. So it's a logistic regression. So yeah, it's a local gradient descent with respect to some of smooth function, and these are logistic losses with respect to some standard data sets. So I don't remember, there is maybe mushroom or some standard data set for logistic regressions. But in the paper, there are other cases. So there is cyclic. There is a case of cyclic gradient descent applied at every node, and maybe other illustrations as well.
Okay, thank you.
All right, so any other questions? So how about, Samuel, we allow everybody to unmute themselves and just ask whenever they feel like asking.
Yeah, so if anybody wants to comment, you can unmute yourself. It's on. I turned it on right after the talk.
Okay, you already did. Okay, that's not really a question. As a thank you from Mary. Thank you for participating.
Thank you.
Okay, so let me ask some more questions here. Right. So in this, okay, let me ask something else then. Okay. So you say that adding variance reduction or client drift reduction, or whatever one may call it, might be problematic. So why do you think so? Why do you think this might be an issue here?
It seems to me that it's antagonistic to this mechanism of doing local steps. So my intuition is that if we apply repeatedly local steps, so of gradient descent steps, for instance, so qualitatively it's a bit similar as applying the proximity operator of the function. So if we apply gradient descent repeatedly, we will converge to the local minimizer of the loss function. So, and we can apply the proximity operator with a variable parameter. If the parameter is small, it's a small step. If the parameter is large, we will also achieve the local minimizer of the local loss function. So, and there is an algorithm which can compute the minimizer of a sum of functions using the individual proximity operators applied in parallel. It's a parallel form of the Douglas-Fatchford algorithm. And its rate, it can be interpreted as a primal dual algorithm. And there is a trade-off. If you accelerate convergence on the primal variable, you slow down the convergence of the dual variable. So at the end, it will converge. It will become the limiting factor, and then the algorithm will not converge faster. So there is a trade-off. This proximal parameter should be chosen in such a way that globally the primal and dual conversion speed is the same. So it's here the dual variables would be kind of the control variates which are used to compensate for this drift. So if you want to
Right, but
of the
in
drift,
the case of, let's say, scaffold or these other newer client drift reduction mechanisms, it works, right? So what happens is that you don't really affect the convergence rate. You keep the number of local steps fixed, but you remove the neighborhood. At least in some regimes, you remove the neighborhood. So it works at least for some operators, right? So why are you skeptical it wouldn't work for general operators?
So here the acceleration factor is always equal to, we always have this acceleration factor. The price to pay is in the drift, but the speed itself can be arbitrarily, so the algorithm can be arbitrarily fast. Up to the point that if the number of local steps is infinite, then the algorithm converges in one step, but it converges to the average of the local minimizer, which is not what we want.
But somehow this client reduction mechanism, in some sense, one way to interpret what's happening is that these local operators keep changing. So one doesn't apply the same local operator Ti h times, but the operator evolves. And in some sense, all of these local operators converge to the same local operator. So somehow you get to the homogeneous data setting, and then you can apply the local operator any number of times. It doesn't matter, right? So somehow this is how these mechanisms should work.
But I guess in the convergence rate, then you have somehow the homogeneity now appears in the rate.
Yeah,
there is some notion of
and it appears by removing the S, right? So somehow it appears by the neighborhood disappears, right? Okay, well.
So it seems to me that I have the intuition that some asynchronous mechanisms would be more helpful to reduce communications than this this algorithm, which is synchronous. So all clients communicate at the same time. I think making it asynchronous for the same communication probability or frequency can.
Yeah, surely, but that's a different mechanism, right?
Yeah, it's a different mechanism. Yeah.
Right. Thank you.